Hello everyone, welcome to this e-module on postulates of quantum mechanics. I'm Dr. R. Niranjana Devi, Assistant Professor, PG and Research Department of Physics, Fatima College, Madurai. Today, we are going to explore the postulates of quantum mechanics. Classical physics work beautifully for large objects, but when we look at atoms and electrons, it fails. Quantum mechanics provides a new framework built on a few fundamental postulates. These postulates are the foundation of everything from atomic spectra to quantum computing. The first postulate says every physical system is completely described by a wave function, usually written as psi of x comma t. This wave function contains all the information about the system. Unlike classical mechanics, where we specify position and momentum, here the wave function is central. For example, a free particle has a wave function psi of x comma t is equal to a exponential of ikx minus omega t. Notice that psi is not directly observable here, but it encodes probabilities of outcomes. The second postulate tells us every observable quantity corresponds to a linear Hermitian operator. Position is represented by the operator x. Momentum is represented by the operator minus I h cross dou by dou x, and energy by the Hamiltonian operator h. Here, why Hermitian? Because Hermitian operators guarantee real eigenvalues which match physical measurements. This is how mathematics ensures consistency with reality. Let's see the postulate 3. The third postulate is about measurement. It says the only possible result of measuring an observable is one of the operator's eigenvalue. The probability of obtaining a particular eigenvalue depends on the wave function's expansion coefficients. For example, if psi is expanded in terms of eigenfunction of momentum, the probability of measuring a certain momentum is mod psi square. The average or expectation value of an observable A is given by expectation of A is equal to integration of psi star A psi dx. The fourth postulate governs dynamics. It says the time evolution of the wave function is determined by the Schrödinger equation. I h cross dou psi by dou t is equal to h psi. This is the quantum analog of Newton's law. If you know the Hermitian of the system, you can predict how the wave function evolves in time. For example, in a particle in a box problem, solving this equation gives quantized energy levels. The fifth postulate is the principle of superposition. It says if psi1 and psi2 are solutions, then any linear combination A psi1 plus B psi2 is also a solution. This is what makes quantum mechanics so unique. States can exist in superpositions leading to interference patterns and phenomena like entanglement. The double slit experiment is the perfect illustration of this principle. To summarize, systems are described by wave functions. Observables are represented by operators. Measurement yields eigenvalues with certain probabilities. Time evolution follows the Schrödinger equation. States can exist in superposition. These five postulates form the backbone of quantum mechanics. They explain atomic spectra, tunneling, laser, and even modern quantum technologies. First, we will see about atomic spectra. When electrons in atoms jump between energy levels, they absorb or emit photons of specific energies. This gives rise to atomic spectra, unique fingerprints of each element. For example, hydrogen shows distinct spectral lines like the Balmer series. These spectra help scientists confirm quantized energy levels and are used today in astronomy to identify elements in distant stars. Next is quantum tunneling. Classically, a particle cannot cross a barrier higher than its energy, but quantum mechanics allows a small probability that is tunnels through. This is called quantum tunneling. It explains phenomena like alpha decay in nuclei and is the principle behind devices such as the scanning tunneling microscope. Without tunneling, nuclear fusion in stars would not occur. Next is laser. Lasers are a direct application of quantum mechanics. They rely on stimulated emission, where an excited atom, when struck by a photon, emits another photon in phase with the first. This produces coherent monochromatic light. Lasers are used in medicine, communication, industry, and even everyday devices like barcode scanners. Finally, quantum computing. Yes, of course, quantum computing harnesses superposition and entanglement. Unlike classical bits that are 0 or 1, qubits can exist in combination of both. This allows quantum computers to process information in parallel, solving certain problems much faster than classical computers. Though still developing, they promise breakthroughs in cryptography, material science, and drug discovery. So, atomic spectra reveal the structure of atoms, tunneling explains nuclear and electronic processes, laser gives us powerful light sources, and quantum computing points to the future of technology. These examples show how the abstract postulates of quantum mechanics translate into real world impact. Finally, quantum mechanics describes the behavior of matter and energy at microscopic scales, where classical physics fails. It is based on key principles such as wave-particle duality, quantization of energy, and the probabilistic nature of measurement governed by the Schrödinger equation. The theory introduces fundamental limits like the Heisenberg uncertainty principle, which restricts precise simultaneous measurements of position and momentum. Quantum states are represented by wave functions whose squared magnitude gives the probability of finding a particle in a given region. Overall, quantum mechanics provides the foundation for understanding atomic structure, spectroscopy, and modern technologies like semiconductor, laser, and quantum computing. Let me conclude this session with a beautiful thought. Quantum mechanics does not just describe nature, it reshapes our understanding of reality. Thank you. We shall meet in the next module.